2017, November 2017 to be exact, I founded Q-CTRL based on almost 20 years of work that I had done as a researcher in the field of quantum science, most recently as a professor of quantum physics and quantum technology at the University of Sydney. And in this if that's the kind of thing you're after. Now, the reason I want to share that message is because I'm extremely excited about this field. I've dedicated my entire professional life to building this kind of technology since I was an undergraduate student in the United States. And I've dedicated this much of my life, you can see I've become one of the gray eminences now, is that quantum technology is likely to be as transformational in the 21st century as harnessing electricity was in the 19th. And if you've seen me talk before, you've probably heard me say that. And I repeat it not just because it's a catchy phrase, but because it's true. And it's, again, not just because quantum is the newest and shiniest thing, it's because there are deep parallels in the way we learned to access and then harness electricity in the 19th century, and how now we're learning to access and put to work quantum physics. Well, with that intro, it's useful to get some perspective. Many of you will have seen this before. This is the Gartner hype cycle. This is a way that Gartner, an analytics company, evaluates emerging technologies. In 2017, for the first time, quantum computing, which is one application of quantum technology, appeared on the hype cycle, on the innovation trigger. It stayed there in 2018. It actually fell off the whole table in 2019. And we're hopeful that in 2020, if it reemerges, it will still be on the innovation trigger and not the peak of inflated expectations or the trough of disillusionment. But if you have Gartner writing things like this about quantum technology, maybe it's helpful to get a feeling for what really this technology is about. And for that, we need to take a step backwards. We need to start here. This is a photograph of microprocessors. These are the fundamental information processing systems that we employ and that have brought us the information age. They're driving the laptop that's being used to run this presentation. There's 6 of them in your car at least. This is the technology that gives us all of the innovation we see today. And believe it or not, it works because of quantum physics. These devices are based on a kind of material called a semiconductor. A semiconductor is a material that can either behave like an electrical conductor, like a wire allowing the flow of electricity, or it can behave like an insulator, blocking the flow of electricity. And you can switch between those two using another electrical signal. Controlling the flow of electricity with electricity comes to us because of quantum physics. And using that understanding, we've been able to build some really amazing things. The most advanced microprocessors today allow you to put literally over 1 billion active devices called transistors in an area roughly the size of your thumbnail. 1 billion. But as impactful as this technology has been, it really involves only the most superficial access to the quantum world. The way we build this kind of technology is a little bit like this. We start with a giant pile of stuff, and by learning the right rules, we shape that stuff into the form that we want. Now, you can do some pretty amazing things. Here you have a sand sculpture with Freud and his patient on a couch. I'm sure you've seen these pictures of crazy sand sculptures. People build magnificent artwork out of this. Things as magnificent as putting 1 billion switches in an area the size of your thumbnail. But it shouldn't escape your understanding that if instead of looking at technology development like this, instead of starting with a giant pile of stuff, if instead we could look more closely, we would see that a new level of complexity emerges. That when we can see the individual grains of sand, they are not a homogeneous tan. Some are transparent, some opaque, some are dark, some are light, some are seashell, some are stone. None of that is visible to us when we only look at the giant pile. It's only when we look closely enough that this complexity emerges. And the same is true in building technology, where today what we're thinking about in what's called the second quantum revolution is finding our grains of sand in the individual particles of matter and light that make up the universe, and starting to build technology here. Now, before any of you scoff at the notion of building technology from single atoms, let me show you this. This is a photograph of one atom in a trap in my laboratory. This is not any kind of electron micrograph or any funny thing like that. It's a photograph taken with a camera that's almost the same as the one in your mobile phone. We shine on laser light of just the right color, the light bounces off, and it's collected by a camera. And it lives in a special electromagnetic bottle called an ion trap. This is our grain of sand. And when we can access nature on these scales, there's new complexity that emerges. Because the picture that you and I have intuitively about the way atoms, these fundamental constituents of matter, might behave, has to be thrown away. It is not correct. Instead of thinking of billiard balls that bounce off one another, we have to think about particles of matter more like waves. Waves that spread out in space through something known as superposition. Waves that interfere with each other, giving peaks and troughs, like in water. And on these size scales, nature even seems to have magic properties, where through something called entanglement, quantum mechanical particles can be linked together, such that even if you separate them by the distance of the known universe, manipulating one will instantly affect its partner. This was all thought to be really strange math for the better part of a century. And none of this is in use in the most advanced technologies that we have today. But starting in the 1980s, some of the leaders in the field, like Wineland and Harosh, got us down to access these individual grains of sand, to access these fundamental building blocks of light and matter. And they showed that the complexity that we predicted in the math is real, that it's really accessible. And since about the mid-1990s, our community has been working to now put this to use as a new resource, to build this new kind of technology that we call quantum technology. In order to understand how we're going to go on that road, how it is that our now emerging industry is looking to build this kind of technology, I want to pause for a second and distinguish two words that sound really similar, or that are at least used synonymously, between technology and tech, because they are not the same thing. We say them interchangeably, but they are not the same thing. When we think about technology, we're thinking about some new capability, like quantum technology, or like the internet, or something like that. Tech, the consumer-facing industrial part of offering or building a technology, is really the tip of the iceberg in this cliche. There is so much more that goes into realizing this technology that we almost never talk about. Because it's really easy to see the stuff above the surface, and not so easy to see the rest. What lies beneath is a combination of research in, say, academia or industry or in other public sector labs, and deep tech. And deep tech is what I'll spend the rest of this talk focusing on. If you've never heard of deep tech, I thought for a little while about how to distinguish deep tech from the tech in quotations there. And it's pretty much impossible to distill this into any small series of bullet points that fits on one slide in a meaningful way that's 100% accurate, but I gave it a shot. And I wanted to talk through this because the distinctions between these two different parts of the technology development ecosystem are really important. If we're talking about tech, we're generally talking about things that leverage existing capabilities. We see a gap in the market, we see an opportunity, and we use existing knowledge and technical capabilities in order to solve a problem of commercial relevance. Sometimes that comes from commercial off-the-shelf components, maybe it's done via open source, but it's always using existing knowledge. In general, you'll be accessing a market that's well established. Maybe you're disrupting a market, or maybe you're offering something new in, say, e-commerce or the like. And the key thing in tech, and especially the VC-based business model, is rapid scaling. Building technology that can be distributed to a very large number of users in a short time.